Okay, so we're going to finish up our gases unit today, and where we left off last time was dealing with partial pressure. And that Pogel packet on partial pressure, well, maybe initially a little too simplistic, will walk you through some aspects of partial pressure that you did not learn in honors, okay? So we're going to close out our learning goal today. Last time we did, in this class, talk about how to do the stopcock type problem. You'll see one of these on the multiple choice section of your quiz. There's a problem like this in your homework at the end of the chapter in the textbook, the $133 book sitting on your desk that you should open. And there's a question like this, I believe it's number 9, bless you, in part 3 of your practice quiz. So if you do both of those and you've gotten them right, you're good to go on this concept. And if you haven't, there are probably more problems that I didn't assign in the back of the textbook that you'll want to explore. So the other thing we want to do is, when we talked about partial pressure, we said you could very easily calculate it using the ideal gas law, PV equals nRT. And you would put the number of moles for the gas in question into the gas law formula, and you would be able to solve for the partial pressure. There's another way to solve for the partial pressure. The very last section on the Pogel packet dealing with partial pressure goes into this. I recommend the last section, which is Model 4. This will nail down this particular aspect. Definitely a multiple choice question on your quiz, which is ready to go. All right, in terms of relating mole fraction to partial pressure, the first thing you want to do is review mole fraction. You learned about mole fraction in honors in the solution chapter, where you learned about molarity, molality, and mole fraction. Mole fraction, as it suggests, is a fraction. It's a number less than 1. So what you're looking at here with mole fraction is I'll get my little clicky thingy. If you're talking about moles of solute, it would be the moles of solute over the moles of solution. Now, moles of solution is the solute plus the solvent together. So if you were given mass of both, you would convert to moles, add the two together. Here it's actually going to be even easier. Mole fraction of the solvent would have moles of solvent in the numerator. So the formula you can come up with is, if mole fraction is the moles of the gas in question over total moles of gas in the solution, you can equate this to partial pressure, and that's what's shown here. This shows mole fraction, capital X, which you'll recall from honors, moles of gas 1 over total moles of all the gases together. And you can relate that to partial pressure, because the mole fraction is equal to the partial pressure of gas 1 over the total pressure. And you could get rid of this piece of it and then just solve for the partial pressure being the mole fraction of the gas times the total pressure. Let me walk you through a few examples. The math is useful. The explanation is the key to being successful in AP Chem. In this example, it says, what's the pressure exerted by a mixture of gases? So you want to know the total pressure. That's the first thing you're looking for. They give you moles of the two gases, as well as the temperature and the volume. Then you want to know the partial pressure. That is the partial pressure of nitrogen gas. They're asking for the mole fraction of nitrogen gas. And then ultimately you want to be able to explain why the pressure of one gas is greater than the pressure of the other gas, and why. So let's take a look at all of these pieces that we can approach here. In terms of what's given, this looks really good. In terms of what's given, we've got moles of nitrogen gas, which is 0.250. That's a sloppy O. We've got moles of helium, which is 0.400. We've got the temperature at 300 Kelvin. Don't forget Kelvin or you will crash and burn. We've got a volume of 3 liters. That's everything that's given. Are you with me? Okay, the first thing we want to know is the total pressure. How can we calculate the total pressure?
By adding the partial pressures together.
We could add the partial pressures together. Do we have either partial pressure?
No.
Not yet.
But we can get it.
We could get it.
The volume.
Right, we know that PV equals nRT. We could get the partial pressure of each one. How else could we get it? What's pressure equal to if we manipulate this? But which moles would we use?
Addition.
We could add them together and get the total, right? 0.650 moles is the total, and then we have 0.650 moles. They didn't specify what unit the pressure's in, so let's do atmospheres. And again, some of the kids asked in second hour the other day, well, is R given? And it is. I always do 0.0821. I think it gives it to you as 0.08206. Be familiar with what the AP exam and what I will give you for every assessment. And again, gas formulas are given here, and your constants as well as conversions are given here. So there's quite a bit of information provided to you that you don't need to memorize. Know where everything is, because time will be crucial. The temperature is 300 Kelvin. I'm going to put that decimal point to maintain the 3 sig figs. And I'm going to divide by 3 liters. And this one isn't the most non-calculator friendly, although you could easily guesstimate. And I'm getting a total pressure of 5.34 ATM. But Violet was absolutely correct in saying I could get the partial pressure of each one and then add them, but it did seem like more work.
Yeah,
But
but you also have to find the pressure of nitrogen gas, so I just...
Exactly, you would have found the partial pressure of nitrogen gas right away, so that's perfectly legitimate too. So the next question is to get the partial pressure of nitrogen gas, and you could do it the same way with one substitution for the moles. You would only use moles of what?
Of nitrogen.
Of the nitrogen gas.
Yeah.
If there were, the numbers would be so easy to deal with. For example, if you had this one, and the total number of moles here were 1, then 300 over 3 is 100, times 1 is still 100, times this, you just move the decimal 2 to the right. So it will be, if there is a question like this on part 1, it'll be very easy to cancel and simplify. Back to like, 4th grade, 5th grade math, just with fractions. with the pressure of nitrogen gas, we could go for it this way and sub in. That's one possibility. So we could do that, and rather than writing that all out again, instead of this, we would have had this, okay? .05. Why would the pressure of nitrogen gas have to be less than the total pressure?
Because it's a partial pressure.
It's a partial pressure. The total pressure is not only the pressure of nitrogen gas, but also the pressure of helium gas. Good. All right, now we have these two pieces, and there are two ways to go about finding the mole fraction of nitrogen gas. How do you want to find that? Go ahead, Austin.
Can you not just do 0.250 moles over the total, which is 0.65?
Yep,
Okay. That's easy.
that's one way to do it. So you could do 0.25 divided by 0.65, and that's 0.385. What's the unit for mole fraction? Ew.
Moles per mole.
It cancels, right?
Yeah.
Moles per mole.
Say it again.
What are we looking for with X?
That's mole fraction. You want me to label that? Nitrogen gas. Can you guys read cursive?
Sometimes. Some of your writings.
If it's good for... Right, like on a classwork, you'll see real scrolly scribble. Yeah. You don't enjoy that. Oh, well.
It is abbreviation of that.
All right, but the other way to get mole fraction, and this is the new way, is partial pressure. Let's see if it works. It's slightly different, but close enough. What's the unit? There is no unit. Alrighty? Easy, easy? Now, but this is what I really want you to be able to do. It says, that's too big. It says, explain why the pressure of helium is greater than that of nitrogen. There are more moles of helium than there are of nitrogen gas. With more moles, they're going to exert a greater pressure on the walls of the container. And that's the kind of thing in a multiple choice question, if you might see in a chart-like format, so they'll say the temperature is constant, or they'll show you two temperatures that are the same, just like in the Pogel packet. The volume is constant, and the only thing different is the moles, so clearly they'll exert a greater pressure, because if you have more moles, they will collide with the walls of the container more frequently, and hence greater pressure. Pressure is force per unit area. The other type of thing that you might see, and these honestly drive me crazy, but this is the kind of thing they just love lately. And so what you might see here is an example with a molecular representation or particulate diagram. And it says calculate the mole fraction of gas B. So how would you do that? You have 4 B's and how many? Well,
1, 2, 3.
I think there are 15. I just want to show you one little trick. When you count, one of the reasons that I let you write on almost every single test is I don't want anything any factor other than not knowing the information to affect you negatively. So if I'm letting you write on the test, then write on it. You knew you had 4 of these, slash the other ones as you, oops, my thingy didn't work, there it goes. Slash the other ones as you go so that you don't make a mistake counting, because with particulate diagrams, these little shapes are all over the place and it's not so easy to count. So, you know, good little trick there. So it would be 4 over, what is it, 15? I should have made it 16, because 4 over 16 would be a quarter, or 0.25. So I'm going to throw another one in there. I think it's a good idea, don't you? It'll be easier. Especially if I'm asking you to do stuff without a calculator. Look, there's 16 now. Magic. Alrighty? Perfect. The way that you collect gases is you do so over water. And this is something that you did in honors.
That's the lab I was talking about.
Which one?
The combustion lab.
The who?
Combustion? Or
Did you
collecting-
collect the gas
Yeah,
over water?
yeah.
What did you combust?
Oxygen and hydrogen. That's what I was telling you about a couple classes ago.
You made what?
A pop.
I know, but what substance did you make? What was your reaction?
Hydrogen and oxygen.
You reacted hydrogen gas with oxygen gas? Where'd you get the hydrogen gas from?
I think I don't remember what we did.
Where'd you get the oxygen gas from?
Two reactions. I don't remember what they were.
Did you?
Decom, probably.
It was one of them was like hydrochloric acid, and then something to get the hydrogen. I think it was zinc. And we had hydrochloric acid and zinc.
Okay. I guess I do.
And then I can't remember the oxygen reaction. But yeah. I was recording still.
Yeah, we're recording, but I'm sort of like on the ceiling. Oh, I don't know. Nah, whatever. So you think you generated hydrogen gas by reacting zinc or magnesium with hydrochloric acid? You generated hydrogen gas and then,
Collected it over water. Oh, like over a drop of water.
Oh.
In the middle.
okay, so you collected the hydrogen gas and then what did you do?
We reacted with oxygen in the air, I think.
No, there was 2 generators. There was
There's two.
a hydrogen generator, and then I can't remember what we did. We did an oxygen generator, and then we figured out like what mold
Ratio is
or,
the
like,
best.
different was the best, and then
And then you reacted
and
the
then
two together?
We had like a modified. It was crazy. We took like a modified lighter and had like an electric spark on it. We put it over the electric spark, and we lit it so that it would combust, and it shot across the room.
Cool. Have to find out about that. All right, we didn't do anything so exciting in here, but we did get to play with lighters, and that's always fun for kids who are infatuated with fire. You didn't eat it.
Yeah, the chip.
That's a different experiment. No, that was our thermo experiment. I'm talking about something else.
Oh, the one where we had to put them underwater and
Yeah, I'm talking about
Gabby burnt her hair on the hot plate. That probably was the solubility lab. In any event, when you want to collect gases, you typically do so over water. Because if you just try and collect gases in the classroom, your gas will mix with the air, which is a mixture of gases. So you're going to have a hard time figuring out how much of your gas you actually collected. So when you collect gases, you usually do so over water. So for example, this tub here, known as a trough, would be filled with water. And one way to do this is to fill a graduated cylinder to the tippy top with water, and then you're going to flip it upside down. You don't want to lose any water. And initially, this graduated cylinder has water in it. now what we did is that we put a lighter here, and we pushed down on the trigger, and the gas bubbled upward. Why would it sit atop the water? It's less dense, and it displaces the water out. So some of the water rushes out, and you can collect any volume of gas that you want. So this will be the gas, and this will be the water. However, in addition to the gas you want, you also collect a little what? Water vapor. Because water in the liquid state will vaporize, forming water in the gaseous state, which is water vapor. Water vapor exerts pressure on the walls of the container, but it's very easy to calculate or determine the partial pressure of the water because this is temperature dependent. So if you know the temperature, you know the pressure of the water vapor. The total pressure is equal to the pressure of the atmosphere, that is barometric pressure, which we'll look up on Thursday to see what it is, if the water levels are the same at the end. So at the very end, you will move this graduated cylinder down so that this water level is the same as this. Once you pressurize, then these two are equal. You know this, you can get it off the internet or a barometer, and that's going to be equal to the pressure of the gas you collected plus the pressure of the water. So the pressure of the gas that you collected is equal to the total pressure minus the pressure of the water vapor. And again, this is temperature dependent. So for example, if, I'll just pull the lab from last year, actually did 2 labs involving this.
Did you have to do like PV plus RT to find the pressure of water vapor?
No, because
Did you
it's,
provide it?
yeah, well, what it is it's going to look something like this. And this is in the POGL packet too, so I highly, I looked through those, and a couple of the questions were very simplistic. It's like, what's the x-axis in the unit? And I'm like, oh God, the kids are going to be mad at me for this. But as the packet builds, it really involves thinking. And these types of diagrams are what you're going to see on tests, what you're going to see on quizzes, tests, and especially in May. So the more exposure you have, the better off you'll be. So for example, if you run your experiment on Thursday and it's a little warm in here, let's say 25 degrees Celsius, the pressure of the water vapor will be 3.17 kPa. So exactly, you will know the pressure of the water vapor. And in the lab, and unfortunately you're not going to preview the lab before you do it, because with your test next week and your quiz, that's completely unrealistic. But you'll see that type of question in the pre-lab, okay? All right, so that is how you collect gases over water. And let me show you the question, and this is just taking it to the AP level. Not hard, it's just an extra step. It says a mixture of hydrogen gas and water vapor has a total pressure of 733 millimeters of mercury. If the partial pressure of water vapor is 17.5 millimeters of mercury, so they could give you that, or they could tell you the temperature, and on the table you'd have to get the partial pressure of water, which is something you're all very capable of doing. Calculate the mole fraction of the hydrogen gas in the mixture. So let's take a look here. What was given is that the total pressure is 738 millimeters of mercury. The pressure of water vapor is 17.5 millimeters of mercury. And we want to know the mole fraction of hydrogen gas. How do we approach this? Yes.
Total pressure minus the pressure of the water,
What's that going to give us?
the partial pressure of the gas, and then divided by the original volume. The original pressure, 738.
Right, the original pressure is correct. So 738 minus 17.5 is 720, no decimal because this doesn't have 1 millimeters of mercury. And then to get the mole fraction of the gas, we're going to do 720 millimeters of mercury over 738 millimeters of mercury. Those cancel, and you've got 720 divided by 738, which is going to be very large. What would have been the mole fraction of the water?
0.02.
0.024?
Yeah.
Yeah. Okay. Piece of cake, right?
Yeah.
All right. The next piece is going to lead into the Maxwell-Boltzmann distribution. This is a little funky. For those of you who are in AP Stats, you'll probably have seen these type of statistical curves. So it might be a little easier for you. It looks really hard, but there's just a few pieces that you really have to be comfortable with. So with the kinetic molecular theory, let's go back and review that. In regard to the kinetic molecular theory, at the beginning of the chapter, we said that gas particles are very, very small and they move in a straight line fashion. Being so very small, their volume is assumed to be negligible, which is pretty meaningless. And negligible is a word that you could see in May, and a lot of the kids ask me what it means on some of their quizzes and tests, so be familiar with the term negligible. For example, this must represent a solid. I'm not really sure which one. It's some type of diatomic, but you can see the particles are very, very close together and there's no movement. In contrast, if you had gas shown here, the particles are very far apart and moving very quickly in a straight line fashion. As we said, the particles are in constant motion. When they collide with the walls of the container, they exert a pressure. We can see here the effect of temperature. I don't think I have voice on. Here we go. I'm going to bring it down a little. My system pops a little bit and it's not appealing to the ear.
Atoms and gas particles are very erratic. Particles continuously change direction and velocity as a result of collisions with other particles and...
Hang on, let me fix that again. It's just like poppy. Let's try that. If anybody knows how to fix this, that'd be great. Get back.
The patterns of gas particles are very erratic. Particles continuously change direction and velocity as a result of collisions with other particles and with the walls of the container.
The particles do not exert any force on one another. They're not attracted to one another in any regard. They don't repel one another. And this is very important. The average kinetic energy, when you have a bunch of gas particles, is directly proportional to the Kelvin temperature of the gas. If the temperature is constant, all of the gases, regardless of their molar masses, have the same average kinetic energy. Okay, and that is in your notes, and we're going to illustrate that graphically.
Molecules in the gas phase are in constant motion with a
These particles are in constant motion, but what they failed to mention initially is on the left side you can see the temperature is higher than on the right side, hence the faster speed.
kinetic energy. Molecules in the gas phase are in constant motion with a kinetic energy proportional to the system temperature. In this example, gaseous molecules at two different temperatures are separated by a thermally conductive barrier. The greater kinetic energy of molecules on the left is transferred through collisions with the wall to the molecules colliding with the right-hand side of the wall. The result is a decrease in kinetic energy and temperature on the left, and an increase in the kinetic energy on the right. Eventually, the two containers reach a thermal equilibrium, where the kinetic energy and temperature on both sides are constant.
You're holding two balloons of the same volume. One contains helium and one contains hydrogen. Complete each of the following statements with different or the same and be prepared to justify. The pressures of the gases in the two balloons are the same. The volumes were the same.
The pressure is the same.
What other information did they give you? They have the same volume.
Do they give us
So
the
in the
answers?
moles.
Yeah, they give you the answers.
And this is different.
Why?
Because they're getting more masses.
Yeah.
Wait.
Their moles are different because they have different molar masses.
Different.
Oh, they said moles is the same.
No, we said it was different though.
I know, but they're saying it's the same.
Oh, I didn't hear.
In sense, it would be the same.
Does it say that they're all the same?
No, the densities are definitely
If
different.
the densities are different, then it should have been mold. We did it too.
Were the pressures the same?
Yes.
So the pressure was the same, the volume was the same,
No, temperature.
temperature was the same, so the moles had to be the same.
Yeah.
Yeah, because all the other, the R is the same, so the mole has to be, that's kind of a weird little thing, yeah, exactly. All right, let's put it into perspective. This is gonna take about 10 minutes to come together. Not everything in chemistry fits in 1 minute, so have a little patience. I know it's very hard because you guys are super smart and you usually get it the first time it's said. So be patient here. All right, couple things we said already. Average translational kinetic energy is directly proportional to Kelvin temperature. All gases have the same kinetic energy at the same temperature. Again, most likely they're going to give you a table just like they did in the POGO packet. If the temperature is constant, the average kinetic energy is constant. Root mean square speed, we don't cover this anymore. Basically what you need to be familiar with is here, the lower the molar mass, the faster the molecule, the higher the temperature, the faster the molecule. And that I'm going to go into in far more detail with this Maxwell-Boltzmann distribution. I gave you two handouts. The first one is a single page, which I've used in the past. I'm going to push that aside for right now, although we will look at one figure. I want to look at the POGL packet of the Maxwell-Boltzmann. I'm going to open both of them up. And we're going to go through a good number of questions here together, and then you'll finish off the packet. And I have always found this concept to be incredibly confusing until I looked at this packet, and this is the first year I've ever used this packet, and I know some of the questions you find to be a little too simplistic, but as you work through the packet, it really makes you think, and I think more than anything, it links a tremendous number of concepts together. Actually, let's do the packet. I just think it's better. All right, it says, who wants to read? Go ahead. Oh, Tommy, can you see?
Yeah.
Go ahead.
have one.
There you go.
Alright, when a sample of matter is heated, the particles speed up. But what does that mean? Are all particles in a sample moving at the same speed?
Hang on. Do you think they're all moving at the same speed?
If it's heated up?
Yeah.
No, because they have different,
No, it's the same particle, so it's all helium, and you heat it up. Does
Yeah.
every molecule of helium move at the same speed? Let's see. Keep reading.
Do
That's
they all
right.
speed up equally? Does mass affect particle speed? Two scientists, James Maxwell and Ludwig Boltzmann, proposed an equation that should be used to predict the speeds of ideal gas particles, atoms or molecules, at any temperature. Their equation is based on statistics and thermodynamic relationships. It is used by chemists and physicists to predict properties of gases such as pressure and diffusion rates, and it can be used to predict rates of reactions involving gases.
Now, interestingly, when I saw this was coming into the AP Chem curriculum, I'm like, ew. So I went to a physics teacher who I had known for a few years. I'm like, can we go over this? I want you to explain it to me before I try and explain it to the kids. She goes, I don't know what this is. I'm like, oh no. So, but this is golden. It is, I promise. I'm going to make it a little smaller. Check out that model. Helium at different temperatures. Now, what do you see on the curve?
It changes.
What changes?
It gets
It
wider.
gets wider.
Taller. The,
As you go from
number of
left to
particles.
right, it gets stouter, if you
Yeah.
will.
The number of particles decrease.
Maybe.
The particle speed.
All right, so let's take a look. And again, like I said, some of the questions initially, you're like, I'm not a baby. Just bear with it. 1A, what's the variable in unit of the x-axis? Particle speed in meters per second. Cool. Particles of what substance are represented in the graph? Helium. How many particles are represented?
1
million.
1 million. What temperatures are represented?
Negative. Is that negative?
It is negative 100,
100 degrees.
100, and 500. According to Model 1, do all gas particles in a sample move at the same speed for a given temperature? Justify your answer with evidence from Model 1.
Okay, so like, if it's at negative 100 degrees, they move at different speeds as the number of particles increases, they start moving. I don't know how to explain it.
Right, it's kind of tricky. It
Yeah.
looks like nothing you've ever seen before. So let's consider this. The range of speed at negative 100 is from 0 to 2500.
Yeah.
So
The
they
temperature's
don't all
constant
move
though,
at the
right?
same speed. And the temperature's for negative 100, so it's constant for that curve.
Okay.
No,
I see it.
Most of the particles move at about 900 meters per second, right?
Yeah.
Because here's the peak right
Yeah.
here. So about 950, well, no, that's more like 980 particles out of 1 million move at 800 meters per second. Oh, about 360 particles out of 1 million move at 1500 meters per second. So not all the helium particles at negative 100 degrees Celsius move at the same speed. Okay? we're gonna figure that out. How many gas particles, this you can read off the graph.
Wait, I have a quick question.
Yep.
If it has 1,000,000 particles for each line, then like how's the first line like so tall and the other one?
No, it's out of, you have a million particles total,
Out of the 3 line. Okay.
out of everything. 1,000,000 particles, and you're tracking the particles at different temperatures.
So that's why it's not points, it's a line.
It's a distribution.
Okay.
Okay, so let's do one of these. According to Model 1, approximately how many gas particles in the sample are traveling at 1,000 meters per second for negative 100? So you would go up, 950 sounds good. And what about at 100 degrees Celsius? Fewer have that slower speed, right? And what about at 500 degrees Celsius?
Almost like
270, whatever, something in the ballpark. It's not a perfect read. But what happens in terms of looking at particles traveling at 2,500 meters per second? At negative 100, you would have 0. At 100 degrees, you would have maybe 150. And at 500 degrees Celsius, you would have about 350. So what you find as the temperature increases is that more particles can move at the faster speed. Okay? So why is the 500 degrees Celsius curve flatter in Model 1? So this curve, this is hard to flip back and forth, than the negative 100.
So why is it flat?
More are moving faster.
One other thing I also wanted, more of them are moving faster, but there are still some of them that have no particle speed. So what happens here, is the area under each curve the same? Yes, it is. So as more particles achieve this faster speed, the curve moves to the right but flattens out to maintain
The area.
It's melted ice cream.
And it's tricky. And when I first looked at this, and I'll show you the sheet that I used to just give the kids, I was like, all right, guys, this is what they're going to ask, just know it. But I didn't get it. But after working through this packet, I think it made a lot more sense. Yep. Yep. Is the area under each of those 3 distribution curves the same? Yes. So that's the first thing. Do some particles have 0 meter per second speed? Yes. So you always have to start here because some of them never really get going. It's like the kid who's sick in the morning who's not going to school. But at the higher temperatures, particles move faster. And so the distribution moves in the rightward direction, but you have to maintain that. What you find as you increase the temperature is that you find that more particles can achieve these greater speeds. So if you consider, for example, 1,500 meters per second as the speed, only about 370 at negative 100 degrees Celsius achieves that. More particles are going to achieve it here, and then you can see the other temperature as well. And this is a slower speed. So as you go more and more to the right here, for example, here you can see none of the particles achieve this speed at negative 100. You've got maybe 140 particles achieving this particular speed at 100 degrees Celsius, and then finally even more particles achieving the greater speed as the temperature increases. but not all of the particles move at the same speed at the same temperature.
So you would say that the higher the temperature, the more particles that can move?
Achieve that higher speed, yes. And I don't think this is going to be an explanation type question. I think it's going to be an interpretational type, and I'll give you an example.
So like at the same temperature, what causes a particle to move faster or slower?
You tell me.
If the temperature's constant,
If the temperature is constant,
they're gonna.
the particles are going to move, but do they all achieve the same speed?
No.
No. And I've got a little picture for you to see that, and then you're going to answer it.
Well, because isn't the definition of temperature the average?
Average. All right, so the rest of that you can answer. But look at number 9, and this is an interesting concept as well. You're going to warm up the gas. It says, circle the set of drawings below that more accurately illustrates the difference in particle speeds for particles of helium at 100 and 500 degrees Celsius. Justify your reasoning. The longer the arrow, the faster the particle is moving. Okay. Here we've got shorts and we've got all longs. Here we've got some shorts and longs, and here we've got more longs than shorts. So it's going to be,
That one, yeah.
and that's your question here. This little picture, I saw a question on an AP exam. So these little diagrams, it's easy once you get it.
Yeah.
But let's take a look. This gets into normal bell-shaped curves, which we look at for grades. This is a right skewed. This is very statistical. But again, you have to maintain touching at that origin here. And you'll work through that piece. And we'll have time in the second half. I don't want to do the whole packet with you because you need a little practice. But here, is the temperature constant?
Yes.
Yes, it's 100 degrees Celsius. And what are we looking at here?
The different.
The particle speed for different noble gases. Now we know the greater the molar mass, the slower the gas moves. And we're going to take a look at that with diffusion and effusion in just a minute at a higher level than what you saw in honors. So this gas here is helium. More of its particles are achieving a greater speed than xenon. And that's because why? Helium has a smaller molar mass. The particles achieve a greater speed. And again, you can work through this, but I really want you to look at the pictures, because when I wrote your test, I just went in, I grabbed one of the pictures, and you're going to have to interpret it.
So helium's achieving a higher speed, but not
More of the particles are achieving a higher speed, because if you consider xenon, none of xenon's particles achieve a speed of 1,000 meters per second, right?
Yeah.
Because this one curtails right
Oh, okay.
here.
Okay.
Yeah.
I get it. Alright.
It's a very tricky concept. And then this one you could do as well. This is a great question. I didn't have you draw in, but this could be a part 2 question. I didn't do it on your quiz. Consider the distribution curve below for fluorine at 100 degrees Celsius. Sketch an approximate distribution curve for chlorine gas at 100. So, fluorine's in period 2, chlorine's in period 3, both diatomic. Which one's heavier? Chlorine.
So
it'd be
it'd be
kinda
more
like-
spread out. It'd be like down low.
More-
So you're going to push it here?
Yeah.
No!
No, it's closer.
Oh, it's
Yeah.
Tricked ya. Because it's heavier, so that's going to be more like the xenon, right?
Oh.
Oh, but as you go through the packet, you're going to work through that. And then this picture is cutesy too. They're all cute. Kinetic energies, we know that the particles can achieve a greater speed at the higher temperatures. That's what we saw already. But this distribution is actually a little different, and you'll take a look at that. But what I really want to illustrate is right here. If the particles are at the same temperature, what can you say about their kinetic energies? Same. So if you see a table on your quiz and the temperature is constant, the kinetic energy is the same. And, yep, I'm
Can
listening.
you go back up here? The one that was like,
The one that bothered you?
no, higher.
Higher?
Isn't all their temperature the same?
Yes.
So why isn't there kinetic?
Particle speed.
This was speed. The other was
Oh,
kinetic
okay,
energy.
kinetic,
The why, and then again, when you work through this slowly, right away they're going to signal you to the x-axis. And everyone laughed at that first little, oh my God, they must think I'm a retard. But no, no, no. They want you to focus in on what the x-axis is. And you'll take a look and work through the rest of this. It's cutesy. I stopped at, we'll stop at page 6. But again, this is just all more of the same, and it's very good. The only thing I used to give the kids was this sheet. This was all I could find on it, and it's in your book just in pieces, and it's kind of murky. So we used to read through this, and I would show the kids the graph, and I would just want them to imprint it in their brain. And I explained that the area under each curve was the same. As the temperature increases, you can see that more of the particles achieve the greater speed. And the kids were like, okay, I've got it. And they could answer the questions. It wasn't an issue, but they really didn't understand it. We'll talk about this aspect more in the kinetics chapter. But I want to show you a question that appeared on a practice exam, and you can all answer this. It says, the graph above shows the speed distribution of molecules in a sample of a gas at a certain temperature. Which of the following graphs shows the speed distribution of the same molecules at a lower temperature as a dashed curve? So that's what they give you up at the top, and you want to see at a lower temperature. Now right away you know it's not C, correct? And B, that looks like a catalyst, right? You're between A and D. JJ, read the question carefully now and tell us the answer.
It's D,
Why?
because it is lower temperature.
It's at lower temperature and fewer of the particles achieve the greater
Fewer than
speed.
right?
All right?
However, more of them achieve the lower speed.
You got it. And then the other question with the little sticks, like the arrows, I have to find that one. I'm not sure exactly where that one is, but that one too is something that appeared. So these Pogel packets are really very, very helpful. All right, we have a couple of other things to do. I'm guessing it's going to take 10 minutes. You want to finish or you want to break?
What's after finishing?
The only reason I'd like to finish is we're filming, and I'd like to, it just runs, so stand up, quick stretch, don't strip like JJ's doing. I wanted that on film because it's funny. I have like maybe 5 to 10 minutes of stuff, and it's really easy. I promise. All right, break's over. Here we go. All right, you'll get a bigger break afterward. Here we go. Just because you took your clothes off, he doesn't have to take his off. My God. Leave the poor kid alone. He has no internet. He has no nothing. He's living in the 1980s. It's going to kill him. All right. They're going to watch this. They're going to be like, what did you guys talk about? Okay. Diffusion and effusion. Talked about diffusion and effusion in honors. All right? I'm going to tell you what you need to know. You don't need to be able to do all the math.
That's easy.
Of course it is. Let's say, for example, who wants to be the stinky one today? All right. So JJ just cuts the nastiest fart over there. And who smells it right away? Whoever's the closest to him, especially if his, yeah.
Kinda like
Okay.
the lab.
So,
Blast zone.
those gas particles diffuse from high concentration, where JJ cut it, to lower concentration. They diffuse out.
Or it doesn't smell as bad.
Right.
It's weaker
Kinda
the
like the
farther
lab.
it goes out.
With like the last
So like,
titration.
and the further the spark goes, the less
It did smell?
smells.
Yeah, a little
Your
bit.
titration smelled that?
Yeah. Yeah, it smelled weird.
No, she didn't fart. Take a look. This is really, really cool. You're going to love
I have
this.
something to know about it.
I'll find it. I don't want to miss it. All right. So diffusion, movement of particles down their concentration gradient. Effusion, I'll hit in a minute. Check out diffusion. This is very, very cool.
Diffusion is the process whereby molecules of gas move to completely occupy a space, giving a uniform partial pressure. In this
Why is ammonia diffusing at a faster rate than hydrogen chloride gas? It's diffusing slow, it's diffusing faster. It has a lower molar mass. This will be about 17, this will be about 36. Now watch what happens when they meet.
example, gaseous ammonia and hydrogen chloride diffuse through air from either end of the sealed tube. When the two gases meet, a precipitation reaction occurs, forming ammonium chloride. The mass of the hydrogen chloride molecules relative to those of ammonia is greater. Thus, hydrogen chloride molecules travel more slowly.
All right, and you saw where that solid formed. It formed much closer to hydrogen chloride than it did to ammonia because the hydrogen chloride molecules diffused at a slower rate. All right, so the heavier it is, the slower it moves.
Would that be a conceptual question?
It could be, or I've seen one like this as well, and I'll pull it up. It could go either way here. I'll pull it up in a sec. A fusion is going to look something like this. You're going to have a pinhole-sized leak, and you're going to look at which particles move outward the fastest. And again, the ones with the smaller molar mass are going to do so.
Diffusion is the process of gaseous atoms flowing into a vacuum through a hole in a container. The rate of diffusion of gas molecules at constant temperature and pressure is inversely proportional to the square root of the molar mass of the gas.
So the lighter ones are going out first.
Correct. And that gets into Graham's law of effusion, which you saw last year. I'll go through the conceptual piece of this. The rate at which the first gas effuses over the rate at which the second gas effuses is equal to the square root of the inverse. So again, the heavier, that is the greater the molar mass, the slower it effuses. So if you have two gases, let's say you have helium gas and argon in a container, and there's a prick hole, which one escapes faster, the helium or the argon? The helium, because it has a smaller molar mass and therefore has a greater rate of effusion. So right here it says which effusions faster when the two gases are compared under the same conditions, nitrogen gas or argon. Nitrogen would be 28 grams per mole, argon would be about 40. Nitrogen. The only other piece I want to mention, I'll give you an easier example to do in your head. Let's say you had helium, which has a molar mass of 4 grams per mole, and argon, which has a molar, no, let's not use argon. Let's use methane at 16 grams per mole. Okay, so which one effuses faster? Helium. How much faster? No, 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 no. So you know this one's going to a fuse faster, so you're going to set this at 1 meters per second. You're looking for this one it doesn't need to go in the equation. So the velocity of helium, I don't know why I made such a big HE. The velocity of helium essentially would just be the molar mass of methane over the molar mass of helium. You are correct.
But it's 2 times.
All right? So helium moves at twice the speed that methane does.
Could it ask how much methane? How much slower?
Always set the slower one at 1. It's easier. I don't know, in this day and age of calculators, and I'm not making fun of you, I'm truly jealous of all the things you have that we didn't have growing up. I don't know if you know that the square root of 2 is 1.41. Do you?
To be honest, yeah.
Do you know this one? I think it's that, isn't it? Who said that? 1.73, that's what I thought.
How would you find square root without using a calculator?
You memorize it.
Well, but it's not hard, right? The square
Yeah,
root
so
of
it has to be
1
available.
is 1, then you have 2, then you have 3, and what's the square root of 4? 2. So it's got to be between 1 and 2.
Well, like, how would you figure it out without a calculator? Like, if it was like a number like 13 or something, you know what I mean?
Same thing. You know it's going to be a little bit less than the square root of 16, which is 4. Okay.
You're just gonna keep multiplying, dividing. until you
Is
find
there a
it.
whoosy whatsy?
It's a seriously long process on how to actually do it.
Oh, I'm sure there is.
But I think on our 7th class, teacher tried to teach us how to do it without a calculator.
As long as you break it into like this like tree thing, you try to pull out.
That's for prime.
And I was
For
so
factors.
It probably is. Shh, Laura. 1. If I move 5 times as fast as you, set yourself at 1 and set me at 5. Because if you set yourself at 2, I would be 10, but then you'd just have to divide at the end. So always set the slow poke at 1. All right, last piece of the puzzle. This also is really easy, and I've got a good way for you to remember, and then you're going to have about a half an hour to nail down gases. All right, we've talked about ideal gases. You know the ideal gas law is PV equals nRT. However, under certain conditions, gases do not behave in an ideal fashion. Rather, we say they are real gases. Those conditions match the conditions in this classroom perfectly. It is always freezing in here, low temperature, and there's no class that has more pressure than AP Chem. So at low temperature and high pressures, gases are real. They're least like ideal. They deviate from ideal. There's lots of different ways you can word this, and we'll go through some of them. In terms of what it has to do with, this is not going to fit together very well till we talk about intermolecular forces, so we'll come back to this concept in a bit. But at very high pressures, what can you say about volume? It's pressure and volume are inversely related. So at high pressure, the volume is lower. And as a result, the molecules are closer together. They get squished. At low temperatures, what can you say about speed? Slower. So they move slower, and now where initially they exerted no interaction on each other, if they're moving super slow, they start to have some type of connection. And as a result, the gas is considered to behave in a real manner. We'll talk about those intermolecular forces later on. You don't have to know how this is adjusted. What you're looking for are 2 concepts here. The greater the molar mass, the more deviation from ideal behavior. That's because it would move slower. Some intermolecular forces would be established. So the greater the molar mass, the more real it is. Which of the following gases deviates goes against
So we
ideal behavior. So which gas would be most real and why?
find the heaviest one.
The heaviest one, the one with the greatest molar mass.
'Cause it's like
If it had said which gas is most like ideal, it would have been hydrogen gas, the one with the lightest molar mass. Look at this. Which of the following best illustrates a real gas? Those are the conditions in here, real life.
D.
Low temperature,
No,
high pressure would be,
D. B. Yeah.
yeah, 0 degrees is a lot colder than 100.
So low
Ask
pressure-
Mariana, she grew up in Alaska. She'll tell you how cold it is.
Low pressure, high temperature. You just wait. Low pressure.
If something's real,
I mean,
it's
high pressure, low
right.
temperature. My bad.
Low temperature, high pressure. But understand the wording. This could have said which of the following best illustrates a real gas, deviates most from ideal. There's a lot of ways to say that. Be comfortable with all of them.
You can tell which one deviates just by looking at the temperature and pressure. You have to know what the molar.
No, just from temperature you would, just from TNP you would know. Molar, it's not going to be both concepts together to the best of my knowledge. It'll be one or the other.
We gotta practice.
All right, so this is going to finish up gases, and what you want to work on in the second half. Look at the Maxwell-Boltzmann-Pogel packet, the practice quiz. All right, and I know some of this is going to get swept under the rug till Tuesday. So unless you're having lab group issues, I would say the next half an hour you should work on gases, and then gases will be put to bed till at least Tuesday. The good news is, even though you have more work than you wanted until Thursday,
After that? Or
after that, aside from writing up the gas law lab, which is pretty easy, it won't be so stressful of a weekend. But this weekend has the potential to be stressful. And again, the exam composition is on Edline. It tells you what's on the test exactly and what to look at. Helen has a question.
How are exams like weighted in your grade?
50% of your total grade, you have 2 exams per 9 weeks, so 25% a pop. Those are the makers or breakers. One quiz does not affect your overall grade very much, but a test can. Study.